In this recording, we're going to start out our Unit 15, Trigonometric Identities. Now, trig identities are one of the most critical things to understand when you take calculus, and some of you at some point are going to take a calculus course. This is a good introduction to what you're going to need to know when you talk about trig identities. First of all, what is an identity? Okay, you're going to use your own paper to write down the heading and to write this definition of an identity. An identity is an equation that's used for all possible replacements of the variable. Let's try to illuminate that with some examples. Okay. This is an example of not an identity. All right, we've got an equation here. I'd like you to proceed to solve this equation for x, then play the recording when you've got it. Okay, so hopefully you got that x equals 5. Well, that is the only value of the variable, the only value of x that makes the equation true. There's no others. However, an identity, on the other hand, is true for all possible values of x. Any number you can think of for x, 17, 41.3, negative 19, any fraction, square root of 2. If you add 0, you're going to get that same thing. Try to think of some other equations that are true for any possible replacement of the variable. Maybe you thought of, well, you could multiply by 1. Certainly that works. Maybe you thought of, well, you could divide by 1. That works too. Maybe you thought of, well, any number times 0 is 0. Maybe you thought of, well, I could have a distributive property type equation where we have an expression in parentheses here, and on the right side it's distributed. There's millions of examples, but all those are examples of identities. They're true for any possible replacements of the variable. So, now let's identify some trig identities. We're going to start basic. First, the reciprocal identities. Okay, there's going to be 2 of these. If you remember, this is pronounced secant, and hopefully you remember that secant is the reciprocal of cosine. S goes with C, C goes with S. So secant's reciprocal is cosine, so we write secant as 1 over cosine. You're going to find that we're going to do our best to represent trig identities in terms of sine and cosine frequently, because sine and cosine are like the most basic of trig functions. Cosecant of theta is the reciprocal of sine of theta, so whenever we see cosecant of theta, we can think of it as 1 over sine of theta. In other words, it doesn't matter what theta you're thinking of. It could be 7 degrees, it could be 2 pi, it could be 41.48 degrees. You can sub that in for the theta, and it will make the equation true. Next, we've got the quotient identities. Quotient means a division. Do you remember that tangent is equal to the y over the x back in our box quiz? Well, you should also remember that sine was equal to the y and cosine was equal to the x. So therefore, tangent is equal to the y over the x, in other words, the sine over the cosine. You probably also remember that cotangent was the x over the y. It was the reciprocal of tangent. Well, that just means it's the cosine over the sine. Now I've put a box, it's a crummy box, but it's a box nonetheless. I've put a box around the outside of this. Those are 4 identities that we're going to have on a box quiz in the near future. Not the class you return to, where we're going to do some practice, but the following class we're going to have a box quiz on 7 trig identities. These are 4 of them. I'll give you the left side, you'll write the right side. The other 3 have to do with the Pythagorean theorem. I'd like you to write down on your paper 3 Pythagorean identities. And the first one is, we pronounce it this way: sine squared theta plus cosine squared theta equals 1. Looks very complicated at first, but it's going to become your friend. Let's make sense out of it with this diagram. I'd like you to sketch out this diagram. It's a unit circle. It has a triangle in quadrant 1 such that the hypotenuse of the triangle touches a point on the circle. It's a reference triangle. So I know that that hypotenuse is 1 because it's a unit circle. And I know that this vertical portion is y because it's the y value. It's also the sine because it's the opposite over the hypotenuse. This x right here is equal to the cosine because it's the adjacent over the hypotenuse. Now, can you relate this triangle, this right triangle, to this Pythagorean identity? Think about the name. It's called a Pythagorean identity. Okay? Basically using a squared plus b squared equals c squared, except the sides are sine and cosine. And it's weird how we write it. We write it as sine squared theta. The square is on the function, not on the angle. We're not squaring the angle. We're getting the sine value and then squaring all that. So that's the most critical Pythagorean identity. But there's two others that branch off of that. Okay, version number 2. I want you to rewrite the original one, sine squared theta plus cosine squared theta equals 1. And this time, divide every of the 3 terms by sine squared theta. Okay? Now let's rewrite what we have left. When you divide sine squared theta by itself, you get a 1. When you divide cosine squared theta by sine squared theta, you have to think about what that means. Well, didn't we have an identity that had cosine over sine just now? Why don't you look over in your paper and see what that one was? Oh yeah, that was cotangent, right? So this will be cotangent squared theta. And then 1 over sine squared theta. Well, didn't we have an identity that was the same as 1 over sine theta? Oh yeah, that was cosecant theta. So this will be cosecant squared theta. That's our second Pythagorean identity. Finally, the third one comes from taking sine squared theta plus cosine squared theta equals 1, the original one, dividing all the terms by cosine squared theta. Okay? Rewrite what you think the simplified form of that is, and then play the recording. Okay, so hopefully you got that this one is tangent squared theta. This is obviously a 1. And 1 over cosine squared theta is written as secant squared theta. Finally, there are 2 alternate forms of the first Pythagorean identity. This Pythagorean identity is so important that sometimes we like to rewrite it so that cosine squared theta is all by itself, or sine squared theta is all by itself. So let's think about what math I would need to do. If I wanted sine squared theta to be by itself, and I want to get rid of the addition of cosine squared theta, what math would I do to achieve that? And hopefully you said, well, you'd get rid of the addition by subtracting. So if I subtracted cosine squared theta from both sides, I'd get this version. And then what would I do if I wanted to just get cosine squared theta by itself? Well, I would undo the addition of sine squared theta by subtracting sine squared theta from both sides, and I would get this alternate form of that first Pythagorean identity. I'd like you to jot those down. Those are not to be confused with the 3 Pythagorean identities. Those are numbered here, 1, 2, and 3, and I've got them in boxes. Okay? Put the numbers right down on these guys. Those are the 3. These are not to be written on your box quiz. Those are just alternate versions of the first one. Thanks for watching.